Okay, well, we get started here. So today we will continue with factor analysis. Are there any questions? Okay. So, as I said last time, factor analysis has a lot of terminology, ways to present the model. So why don't we just begin spending maybe 5 to 10 minutes just reviewing what factor analysis is, reviewing the terminology behind it. So again, the goal is to find a set of what we call common factors that explain most of the information that's available in our data. We hope to only need to have, let's say, a few common factors. And obviously we want to have the number of common factors to be less than our number of our original variables. And then also we want to be able to interpret these common factors. So we can see that we have goals that are very similar to what we had with principal component analysis. How we accomplish these goals are different. And so we set up the following model. And again, I presented to you a few different representations of the model. Here's just the most widely used representation, where on the left side of these equations here, we have our standardized variables. And on the right side is our assumed structure about how do these variables, how do their variable values actually come about. So if we take a look at our first, let's call it original standardized variable, Z1, we're saying that's equal to lambda 11, which is a constant. It's a parameter that we want to estimate, times F1, which is our first common factor, then plus another constant, lambda 1, 2, and these constants are called factor loadings, times our second common factor, F2. And let's say, just to be general, we go all the way up to the mth common factor. And then finally we add eta 1, which is called a specific factor to it. And so if we knew those lambdas, if we knew those f's, if we knew those etas, we know what Z1 is. And then we also have a similar equation for the second standardized variable, all the way down to the pth standardized variables. And if we look at just one of those equations, we can see how this is very similar to what we see for a regression model. The differences, well, let's talk about the similarities first. These lambdas are kind of like what we think of as our betas for a regression model. We want to estimate them. These lambdas give us a lot of good information about what these f's actually represent. So if lambda 11 was equal to 0, then that says there's essentially that F1 does not have an effect on Z1. If lambda 11 was positive, it says that F1 has a positive effect. If lambda 11 is negative, it says that F1 has a negative effect. And also then the eta kind of plays the role of our epsilon, our error term, in a regression model. Now, continually talking about this interpretation idea. Now, since we actually have p different equations, and notice how F1 is in each of those p different equations. That's why it's called a common factor, because it's common to all the original variables. To interpret this F1, all we need to do is take a look at those corresponding lambdas. And so, for example, let's say if lambda 11 was 1, lambda 21 was negative 1, and all the other lambdas corresponding to F1 were 0, then we would say, okay, what F1 is representing is essentially a comparison or a contrast between Z1 and Z2. Let's see if I talked about all that. Yeah. And so we can also put these p different equations into a matrix-like form, as I showed there. And because of this assumed model structure, we can actually come up with a representation for our correlation matrix, or equivalently our covariance matrix for the standardized variables. This expression for this correlation matrix is what's called the factor analysis equations. Let me make this a little bit bigger so we can zoom in. And so, and you're not responsible for the derivation about how this comes about, but you are responsible for understanding the components of this expression. So for example, if we look at row sub Z1, Z2, this represents the correlation between the first standardized variable and the second standardized variable. This expression says it's equal to the sum of the product of some lambdas. Now let's go back to our model. Which lambdas are they? Notice when I have a 1 here for Z, I always have a 1 in the first subscript for the lambdas. Look at this subscript 2. Notice in the first subscript for the lambdas, I always have a 2. And so notice I'm looking at Z1, Z2, so that means I'm taking the product then of those corresponding lambdas for Z1 and Z2. That represents the correlation between them. Then on the diagonal elements of the correlation matrix, of course, we would always have 1 there. Why? Well, again, think about it in terms of the covariance matrix for standardized variables. Covariance matrix for standardized variables. Remember that the variance of each standardized variable is 1. Okay? So, look what we have here. So this is kind of like you could say the correlation between Z1 and Z1. Okay, of course it's 1. And so notice, in comparison to what we had before, now we have, let's say, a lambda 1k times a lambda 1k. In other words, lambda 1k squared. But now we also have an additional component, which is the variance of eta 1. And we, again, lots of notation, lots of terminology. Psi sub 1 represents the variance of eta 1. This is called the specific variance for the specific variable. Some people will even also call this the uniqueness as well. And so we have this, we have then, because of our assumed model structure, we have this representation for our correlation matrix in terms of the lambdas and the psis. Some other, and we'll be using this very, very shortly here. Now, something else, we looked a little bit at a derivation of, well, what's the correlation between Zj and Fk? In other words, original variable and one of these common factors. What's that correlation? It ends up being lambda jk. So if we go back to our model, what does that mean for us? We actually do a little bit of erasing. Again, when we're looking at common factor 1, we look at the corresponding lambdas to try to interpret it. But now we have another nice way to think about this, that the correlation between F1 and Z1 is lambda 1, 1. So again, if a correlation is 0, we know that there's no relationship. If correlation is positive, it means that we have a positive dependence. Also, what this means for us, since this is a correlation, each of these lambdas has to be between -1 and 1. And lastly, just another term, there's something called a communality that we talked about before. The communality of the jth standardized variable is the sum of the lambda squared. What does that mean? In other words, you take this lambda squared, this lambda squared, this lambda squared, and you add them up. And so think about that word commonality. What this is essentially measuring is how much how much information is the common factors explaining about a particular original variable. Okay. Now let's go on to then our new material. Okay. We want to be able to eventually estimate these lambdas. Because of this relationship that we have with that correlation matrix, that tells us that if I happen to know the correlation matrix, I have a way maybe to get at to find out what those values of the lambdas are, what these signs are. And as you might be expecting then is that, well, what if I just replace this correlation matrix with an estimate? And then I can solve for the lambdas, solve for the size, and voila, I have now my parameter estimates in terms of our model structure. And this is essentially what happens. But unfortunately, things are not as easy as they may appear. Okay. So our correlation matrix, we use the symbol P to always represent our true correlation matrix. Remember, the estimate is represented by capital letter R. With a correlation matrix, let's say if it was known, then essentially we have P times P plus 1 divided by 2 quantities known in that matrix. Notice I'm using a little p there. And that little p is always what we use to represent how many original variables do we have. Now you might be wondering, well, how does this come about? Well, let's say that p was equal to 2. That means we have 2 times 2 plus 1 divided by 2, which is equal to 3 different known quantities. And if we actually write out that correlation matrix, this is what we have. So I would know this one, I know this, and I know that. Notice the one element of that matrix I didn't highlight is what we had before, because of course, what we have in the 1, 2 element, because the correlation matrix is symmetric. So that's why we know 3 quantities. So we have 3 known values.
That's
Yeah.
2p, 2, row 1.
This right here should be row 2, 1.
P2, P1.
But the thing is, the matrix is symmetric. So that's why I can write that as row 1, 2 as well. In other words, what's the correlation between Z1 and Z2? Well, it's exactly the same as the correlation between Z2 and Z1. And so that's why I wrote it like that, because the matrix is symmetric. So in the end, we don't know 4 things, we only know 3 things. Because these are duplicates. Whatever is in the 1, 2 element will be in the 2, 1 element. Okay. Now, these lambdas are unknown to us. Well, how many lambdas are unknown? Actually, let me go back to what we had here. Go back to our, I think it's easier to see it in this form here. I have p rows, or p different equations. I have m common factors. So that means I have p times m different lambdas that I want to get at. Also, remember with these etas, they each have a particular variance that's unknown to us. So we have p variances that are unknown. So in total, on the right-hand side, let's say, of our factor analysis equations, we have how many unknowns? P times m plus p. For some reason, I just wrote it as m times p in our notes, but it's p times m as well. So, think back to your algebra days, where you had a system of equations. And you had, let's say, maybe you're trying to solve for, let's say, two unknown quantities, you needed to have two separate equations. Three unknown quantities, you needed to have three separate equations. If those numbers don't match up, you can have problems. And in fact, this is what will happen here. So for example, more than one solution may exist, meaning that there could be more than one set of lambdas that actually satisfy our system of equations. Now, I just want to emphasize something. Sorry. So when I say we are going to have a system of equations, what you could basically say is this. I'm going to set this quantity equal to that. I'm going to set this quantity equal to that. I'm going to set this quantity equal to that, and then solve for the lambdas, solve for the size. So for example, let's say that P was 4. So we have we have 4 original variables. And we have 2 common factors in our model. What that means is that we will have 10 equations that we can write out, but we have 12 unknown values. So that can be a problem for us. There can be other problems as well. There could be situations where a solution actually doesn't exist. So previously I just said, well, you can have more than one solution essentially. But you can also have a situation where a solution does not exist. So suppose P is equal to 3, M is equal to 1. This corresponds to a situation where you have 6 equations and 6 unknowns. Hey, that's great. And so here I just wrote out the corresponding matrix. And so again, what that means is that 1 is equal to this. Row 2, 3 is equal to this. I write out 6 equations. And that's what I actually did here. Now, with a little bit of algebra, you can get an expression for lambda 1, 1 squared. Well, how did I do that? Suppose in this, let me highlight. Suppose in this equation here, you solve for lambda 2, 1. In this equation here, you solve for lambda 3, 1. Then you go ahead and you plug those 2 values for lambda 2, 1 and lambda 3, 1 into the last equation there, and you will get this. Okay? Here's the problem that can occur. Suppose my correlation matrix is what's shown there. Notice in the 1, 3 element we have a negative value. So if I put in, row 1, 2 is 0.3. Row 1, 3 is negative 0.3. Row sub 2, 3 is 0.3. So I get negative 0.3 in the end for what lambda 1, 1 squared is equal to. Well, you can't have a squared value be equal to a negative. So a solution does not exist with this correlation matrix. Here's another example. Suppose that this is my correlation matrix as well. So now I don't have any negative values. And if you go through the same way of finding what lambda 1, 1 squared is, you get lambda 1, 1 squared to be equal to 1.44. Now remember, we have an equation, though, that's up here that says 1 is equal to lambda 1, 1 squared plus psi 1. So what you could do is simply put in that 1.44 there. Psi 1 then would have to be negative 0.44. But psi 1 is a variance. You can't have a negative variance. So now we have another problem here. So once we get into actually formally doing the estimation, you will sometimes have R tell you, uh-oh, a solution doesn't exist. And it could be for the reasons that I just told you here. So we have to be on the lookout for that. So now we're getting into now, how do we find these parameter estimates formally? There's a few different ways. I'm only going to talk about the most prominently used way, which is what's called maximum likelihood estimation. Now, maximum likelihood estimation is something that is widely used in statistics. But I also understand that students, when they come into this class, they may not have seen this before. So I'm going to go to a separate set of notes, which I call my MLE supplement that was on my website, that briefly explains what maximum likelihood estimation is, so that we can apply it to this particular problem. So the way that I like to explain maximum likelihood estimation, well, let me back up a second. If you want a little bit of longer explanation, you can take a look at Appendix B of a textbook that I wrote for our categorical data analysis course that I primarily teach here at the university. I also talk about maximum likelihood estimation then whenever I do a mathematical, in terms of, I also talk about maximum likelihood estimation in terms of an introduction whenever I do a mathematical statistics course. So if you look at my Stat 880 notes, you will see another explanation there as well. And the way that I often like to introduce maximum likelihood estimation to students is through kind of an intuitive example. And this deals with the success or failure of a field goal. Now, in your very first stat course, you'll learn about a probability distribution called a Bernoulli probability distribution that's used in situations where you essentially have two possible outcomes for your random variable, which we often say is a success or failure. So like a success for a field goal, failure for a field goal. And this is one way to write out this probability distribution, which should at least have some similarities to what you've seen before. Let's say my random variable y represents the success or failure or field goal, where y equals 0 for a failure, y equals 1 for a success. I'm going to be a little bit more formal in my presentation here, where I use uppercase letters to represent random variables, lowercase letters to represent values that they can take on. If you haven't seen that before, or if you're uncomfortable with it, it's simply a really brief explanation. So my random variable could be 0 or 1. And sometimes I want a symbol to say, well, it's 0 or 1, but I don't want to necessarily always write out 0 or 1 in there. And so in those particular situations, we use the lowercase letter y to represent that. So here's my probability distribution. The probability that my random variable y is equal to either 0 or 1, which I denote as simply little y, or lowercase y, is equal to, let's say the probability of success for a field goal is pi, the Greek letter pi, and we have pi raised to the y power times 1 minus pi raised to the 1 minus y power. So if I simply write this out as the probability y is equal to 0, this would be pi raised to the 0 times 1 minus pi raised to the 1 minus 0, or in other words, 1 minus pi. Probability y is equal to 1 is equal to pi raised to the 1, 1 minus pi raised to the 1 minus 1, or just pi. Okay? And let's say that I go out to Memorial Stadium and I decide to try to estimate my probability of success for 40-yard field goals. And so what do? Well, I take a sample of me kicking the ball. In a general way, let's say I take a sample size of n, or eventually we'll say, how about we just do it 10 times? Perhaps did anybody go to the game on last Saturday? You didn't miss much. The best part of the game was actually, I think it was in the first quarter when the teams were, there was like a TV timeout. So the teams are off the field, and so always in the first quarter they have this contest where, let's say, a randomly chosen fan comes down on the field and they try a field goal, and if they make it, they win $5,000. And the guy made it. That was like the best part of the game. And so I don't know, maybe he was using statistics to try to figure out how best to kick that field goal. And so anyway, so Y1 through Yn, where I'm using the lowercase letters there, represent, let's say, a general way to represent my actual sample that I got. Maybe the first kick was a failure, so I have a 0. So that would be like little y1. Second kick was a success, little y1, I'm sorry, little y2 would be 1. And so given this information, I like to estimate my probability of success. And a formal way to do this in statistics is to start with what's called a likelihood function. And all that a likelihood function does, it measures the plausibility of different values of pi. So is pi equal 0.1 a plausible value for, is 0.1 a plausible value for pi? Is 0.6 a plausible value for pi? And it's formed in a rather intuitive manner here. So first of all, in terms of notation, the likelihood function is a regular mathematical function. We call this likelihood function L. L of pi, it's a function of pi. We use the vertical line here to represent the word given. L of pi given my data, given my information that I observe. And all that it is this. The probability for my first field goal that I attempted, the probability that's either a success or the probability that's a success. I'm not saying that very well. The probability that Y1, capital Y1, which represents what happens on my first field goal, is equal to either 0 or 1. Times, same thing for the second field goal, times all the way up to the nth field goal. And so I could write this more compactly in product notation, where I take the product from I equal 1 to n of the probability that capital Y sub I is equal to little y sub I. Then we can plug in our Bernoulli probability distribution there. So the distribution that we had before, the only difference is now I say, okay, this is for y sub I instead of just y in general. Then I can use properties of working with exponents. So just to make sure you see this. So if I had, let's say, 2 to the third power times 2 to the 7th power, that would be 2 to the 10th power. I just add the stuff that's in the exponent. So that's why I have the sum of the y's and n minus the sum of the y's there. And you can just delete that very last line of that equation there. And so let's say that I actually observed 4 total successes out of 10 different times that I kicked the field goal. And then what I could do now is use this data, use this information to evaluate what my likelihood function would be at particular values of pi. Again, we are using this function to evaluate the plausibility of different values of pi. The larger this function is in numerical value, the more plausible the corresponding pi will be. And so I could put pi equal 0.2 there, and I get 0.000419. I could put 0.35 in there, I get 0.001132. So in terms of this likelihood function, 0.35 is more plausible than 0.2. And eventually you can get to a point where you see that 0.4 has the largest possible value of the likelihood function. And therefore, we would say that this is the most plausible value of my value, most plausible value for pi. And so what we have just found here is what's called a maximum likelihood estimate. And pi equal 0.4 maximizes my likelihood function. One could actually plot it out, and you can see that at pi equal 0.4, indeed, that's where my maximum is reached.
Calculate with the R, yeah? Not with your hand.
I'm sorry, could you repeat that, please?
I mean, for this different part, you calculate in R, not with your hand, yeah?
Say that one more time, please.
This table, you calculate the values with R.
In the end, I did, yes.
Yeah,
Yeah,
not
so-
with your hand, and we don't have to do this with our hand or
No.
something.
So I skipped over the R part here because I feel as though that's not as important. I mean, anybody could do it on a calculator too. And this is more background information so that we can apply it with respect to factor analysis. But I didn't want to hide anything, so that's why I also included the corresponding code. Okay, so that's my maximum I could estimate. My most plausible value for pi, given my data. Hopefully that's intuitive. If I have 4 successes out of 10 trials, my proportion of successes is 0.4. Okay, that makes sense. That's why I choose this example, because it makes intuitive sense. Now, in general, though, the maximum I could estimate can be found using tools that you learn about in your, let's say, Calculus 2 or Calculus 3 course days. When you talked about how do I maximize, or how do I find the value of some function that maximizes it or minimizes it. And so what we could do is as follows. First, we begin by finding the natural log of the likelihood function. Wow, this isn't needed, but this is the way that most people will approach it, because then you can come up with a nice mathematical form for the resulting function, as you will see shortly when we apply it to this Bernoulli example. Take the derivative of this log likelihood function with respect to pi, set the derivative equal to 0, solve for pi, and as long as certain regularity conditions occur, this will be the maximum likelihood estimate.
Why we should find the log? I mean, we usually get that derivative and set it equal to 0.
Yeah, so first of all, using the log is not going to change anything because it's a monotone function. The reason, and I'll just jump ahead. So let's say if I actually wrote out now the log likelihood function. I should say, I'm sorry I didn't say this before. In statistics, typically whenever someone uses log, they mean natural log. Okay? So if I take the natural log of the likelihood function there, notice what happens. So if I had, let's say, the log, we'll just talk about in general first. The log of a raised to the b power, this is equivalent to b times the log of a. And so look what happens for us then, and also, sorry, there's one more thing I should mention. If I had log of a times b, using properties of logarithms, this will be the log of a plus the log of b. So now look what happens with this expression here. When I take the log of pi raised to the sum of the y's times 1 minus pi raised to the n minus sum of the y's, I can first break it up into 2 different components so that I have a plus there now. And then, since this is up in my exponent, I can bring that out in front of the log. And so that's why we end up using the log. Very many probability distributions have something, let's say, up in a power, and so that's why working with the log is the standard. It can also have some numerical advantages as well. So if I wrote it in terms of partial derivative, if I take the derivative with respect to pi, so for example, remember the derivative of log of pi would be 1 over pi. The derivative of log of 1 minus pi would be negative 1 over 1 minus pi, using that chain rule. I set this equal to 0, do a little bit of algebra, and here's my maximum likelihood estimator, the sum of the y's over n, which is essentially what we had before when we had 4 successes, 10 trials. This is just a more general representation. Since this is an estimator, to allow us to calculate an estimate, we always make some kind of symbolic change. Typically, we put a hat on top of the corresponding parameter that we're trying to estimate, to say, hey, this is my estimate, rather than a true value. Okay? So that's a very basic explanation of what maximum likelihood estimation is. We will never need to do anything like this by hand, but it's good to have an intuitive feel for how this comes about. R will actually have a function for us with respect to factor analysis that will automatically find the estimates for us if they exist. Later in the semester, there will be 2 sets of notes where we have to use maximum likelihood estimation again. And again, R will have functions available to us that automatically does the calculations. If by chance you were interested in seeing a little bit of a more complicated example to find a maximum likelihood estimate using working with derivatives and stuff, here's how you can do it with a normal distribution where you're trying to find the estimates for mu, the mean, and sigma, the standard deviation. Also in these set of notes, I have a little bit of a subsection on likelihood ratio tests. We will come back to that. But for now, let me go back to the main part of the notes. So in our particular case, the likelihood function is much more complicated than what we just saw with the Bernoulli distribution. You know, for our case, we have a random sample that results in vectors for each observation. We have x1 through xn. And previously, when I introduced factor analysis, I said, okay, we will have something like this, and we can assume that it comes from a population that has some mean vector, some covariance matrix. To find a maximum likelihood estimate, now we have to assume we also have a probability distribution with this. And what is done in factor analysis is we assume that we have a multivariate normal distribution. So that's why I have the big N there with a little subscript p, meaning it's the x's have p, it's p by 1. And so now my likelihood function becomes this. Here's my parameters. And think of the factor analysis model first written in terms of the x's. Okay? Here are my parameters. I have capital N different observations, so that's why I'm taking the product from r equal 1 to n. And then I just write out my multivariate normal distribution, where I put a little subscript r on the x to represent is for the rth sample value. Now, from looking at that, you might be thinking, okay, well, wait a second. Well, how's our factor analysis model represented there? Where's my lambdas? Where's those size that I want to estimate? Well, they're in there. If we think of the factor analysis equations written in terms of our x's, we have this representation for sigma, our covariance matrix. And so that's how we get our lambdas. That's how we get our size in there. And so what we're going to want to do is now maximize typically the log of this likelihood function, find the values of all the lambdas in the size such that this likelihood function is as big as possible. And that's going to be that will lead us to our parameter estimates, and then we'll actually be able to write out our factor analysis model with those estimates. Now, if I did have standardized variables, which we typically will do, then I just replace the x's with z's. That mu would be just 0. We would know that. The sigma now is going to be represented as, let's say, that correlation matrix is equal to lambda prime plus psi. Now, one is not going to, let's say, try to find the derivatives with respect to the lambdas, set them equal to 0, find the derivatives with respect to the size, set them equal to 0, and then solve it all by hand. The reason why you're not going to be doing that is because it actually takes what are called numerical iterative procedures to actually find what these parameter estimates are. With that, and probably a lot of you have seen this in other places before, outside of a statistics course, where I don't have what's called a closed form solution. I can't just say pi is equal to the sum of the y's over n. I can't say that. Instead, what I'm going to do is come up with, let's say, an initial set of, let's say, parameter estimates. So initial guesses, let's say, for the lambdas in the size. And then I'm going to use a numerical iterative procedure. Maybe, for example, like if you've heard of like the Newton-Raphson procedure. Use this procedure to, let's say, come up with a new set of lambdas in size that are hopefully going to be better, that are going to maximize or make that likelihood function bigger. And then, after I do that, I'm going to compare these lambdas in size to what I originally started off with. If they are extremely, extremely close to one another, then I'm going to say, oh, I must have found them where that likelihood function has been maximized. And so now I'm going to use those as my estimates. If they're not close to one another, then I'm going to put this back into my Newton-Raphson procedure or whatever numerical iterative procedure that one wants to use. I'm going to put that in there and come up with some even better estimates for the lambda, better estimates for the size, and then compare them, these better estimates, to what I just had previously. If they are very, very, very similar, then I must have found where that maximum of that likelihood function occurs. I'm going to use this new set of lambdas in size as my maximum likelihood estimators. If they are not close, then I'm going to keep on doing this iterative process over and over and over again to improve my estimates to find where that maximum value occurs. Now there might be cases where you're doing this many, many times, and eventually you get to a point where, okay, I'm just going to have to give up. I'm not finding it, and that can happen. So when you do find these maximum likelihood estimates, meaning for successive iterations, the lambdas and the size are very similar to one another, the numerical iterative procedure has what's called converged. It has come to a point where things don't change anymore if you keep on doing them. If you keep on doing these iterations again, these parameters are not going to change. You have reached convergence. In factor analysis, you are not guaranteed to actually reach convergence. Okay. Now, finally, after all that, we get to take a look at an actual data example. The main R function that people use to estimate these parameters and do other stuff with factor analysis, the main function is called factanal. Okay? This function automatically always uses standardized data. So you don't have to pass into it the standardized values. It will automatically standardize the data for you. And it will automatically use maximum likelihood estimation. Okay, so let's go to the goblet data. What we will find out later with this goblet data is that two common factors are okay. And so I'm going to use two common factors now, and again later we'll talk about how I came up with that decision. So I read in my goblet data, as we've done before. I make a little adjustment to it to account for the overall height of the goblet data, as what we've done before. And now to actually estimate the factor analysis model, I use the factanal function. The syntax for it is similar to what we saw with printcomp. If you remember, printcomp would say formula equal tilde W1, W2, and so on. Here, instead of using formula, that first argument is x. It's just what the authors of the function chose. So I say x is equal to tilde W1 plus, meaning and, W2 plus W4 plus W5 plus W6. There's an argument called factors. That's where you specify how many common factors you want. You can also specify where your data is. And there's a last argument called rotation. I will explain that more later. For now, let's just use this particular value called none. Okay. I'm going to put the results from running this function into an object called mod.fit2. Where does this name come from? Model fit two common factors. That's why I chose it. I could have chose some other name if I wanted to. Okay. And so now, whenever you, again, approach a new or use a function that you really haven't used before in R, one of the first things that you should do is to use the names function with it so that you can see what's actually stored inside there. Mod.fit2 ends up being a list in terms of R's terminology. And so we see some names of stuff in there that kind of look familiar to us. So converged. This will tell us, hey, did my parameter estimates converge? I have information such as loadings. Remember the lambdas, the formal name for them is the factor loadings. There's that you name uniqueness. Remember the specific variance, another name for it is uniqueness. Correlation as well. We can also use the class function here to see, well, what's the class of this object? Well, the authors decided to call it exactly the same name as the name of the function itself. And so with that then, I can say methods class equal factano, and I can see all the corresponding method functions with this. When we did principal component analysis, we had more method functions. Here we only have one, print. We'll look at that shortly. And then I think this is kind of disappointing how the authors decided to structure this. And so you might, if you remember with print comp, we had a method function called, we had a method function for summary. So what that means is if I said summary, parentheses, the results from print comp, and parentheses, I get a nice summary of what's going on. But here we didn't see summary as one of those method functions. And so if I apply summary to that, I really don't get anything much really useful. But instead what I need to do is just simply type mod.fit2. And this is then what I get. I don't get everything that's inside of what mod.fit2 has. I get essentially my summary that you might expect. Okay, let me actually go back over here to my notes so I can write on this. So we have information that says, okay, how was this implemented in terms of the actual code? Here's my uniqueness. So psi hat 1, the estimated specific variance for the first for the first specific factor is 0.16. I have a table called loadings here. Here's my lambdas. So for example, this is lambda 1, 1. Now I'm going to put a hat on it because these are actual maximum likelihood estimates. Here is lambda 2, 1 hat, 0.494. I did skip over something, I apologize. Come back here. So if I just said mod.fit2 here, this is what I get, which looks very similar to what we just saw. There's one difference. Notice there's nothing there, but, and this was actually what was displayed in the notes, I do have something there. Okay. So by default, R will not print some of the factor loadings, these lambdas, if they're close to 0. I don't really think it's a big deal. Just print it off. I can see that it's close to 0. You don't need to hide it from me. And so a way to deal with that, and this is what I always do, is I take advantage of that method function for print that we saw. I say print, first argument is x, mod.fit2, and then I add an argument called cutoff 0.0. So that means essentially it will print everything, even if it's very, very close to 0. If instead I did this, just to show you how that works, suppose I put cutoff 0.1 there, now we can see how that one value was hidden because the value was negative 0.034. So it was within 0.1 of 0. Now, just so that you understand how R works here, basically whenever you type an object name in the R console here, like mod.fit2, or let's say if I estimated a regression model from, let's say, using the LM function, and I typed, let's say if I called it mod.fit, whatever, I typed that, what R is going to do is automatically look to see, is there a corresponding print function, print method function for it? And it will automatically implement that. So even if I type mod.fit2 here, what R is going to do is look, is there a print function? And if there is, it's going to actually implement it and run it. It's just kind of a weird way that this is how R works. If there wasn't a print function, what will happen is, and perhaps I'm getting a little bit farther than what we need to know, but what will happen is this with a list. It will actually print off the value for converge, print off the value for loadings, print off the value of uniqueness, print all those values off. It will print every single value that's within that list if there wasn't a print function. What? That's a good question. Do you want to say that more specifically in terms of what the?
Because we saw that there were only one function and that was print.
Yeah.
So.
Okay.
There
okay.
No.
So this gets into my introduction to R notes that R is an object-oriented language. Depending upon the class of the object, that's how R is going to, let's say, run particular functions associated with it. So, there are generic functions, there are method functions. A generic function is like summary, like print. A method function is like, in this case, there should be a method function called print.factAnal. Okay? And so when I run the print, and so when I looked at this, I saw that there happened to be only one generic function that's associated with this particular class. And so when I actually now run that generic function with mod.fit2, it finds a function called print.factAnal, and it actually runs that. Now, in general, now, I think this is maybe getting at your question. In general now, for how R operates, again, it will look to see if a particular object has a method function associated with it, associated with a generic function, okay? If it doesn't, it will actually run what in this case will be print.default. And what will happen if, let's say, this print did not exist, it will actually list off all the numerical values corresponding to the 12 different components of this list. Okay?
If
Yeah.
you,
Go ahead.
sorry, if you print like do the print.fact anal, it would be the same as this.
Yes. So we can see that if there's a function called getAnywhere that helps me find where that function is. And we can see that it exists. When I actually tried to run it, it did not work. And this happened about 15 years ago in R. There are ways to limit your access to particular functions because, why would someone want to run this directly? Well, you don't. And let's see if I can get it to work. Okay, so there's a little bit of a trick here. And most people don't see this, or haven't seen this, I bet. So the fact_anal function actually exists in the stats package. And so because of that, you would expect corresponding method functions to also exist in that same package. So if you ever wanted to specifically say, I want this function from this particular package, the syntax is you put the package name, : the method function. And that's why I was able to get it to work there. For some reason, it was set up so that if I only do this, it doesn't work. Now why does R give you this kind of an option? You could have, let's say, multiple packages that are loaded in what's called your search path, meaning that R says, okay, I can look in this package, I can look in this package, I can look in this package for a particular function. These packages may have the exact same function names in them, even though they do different things. And so that's why R gives you an option like that to be able to specify it. So, I guess what I've talked about now for the last few minutes is a little bit more beyond than what we need to know, but I like to talk about it here because I understand that many of you are maybe new to R or don't have a whole lot of experience with it. Any other questions about that? Okay, let me come back here to the notes. Let's see here. Yeah, just to make sure maybe I didn't explain this to you. So obviously we can see those are the original variable names, and notice how we have factor1, we have factor2 there. That's how I knew which lambda was with what. Okay. So a very, hopefully, easy question that I would put on a test would be, okay, go find the factor analysis model for this data, write out the estimated model. So what is the estimated model here? Unfortunately, I can't get this all on one screen. So I write out the z's. Here is my lambda hat 1,1 that I pointed out before. Here's my lambda hat 2,1. I'm writing it all out. Here's my f vector. Here's my eta vector. If you wanted to instead, you would just simply write this out as z1 is equal to 0.555 times f1 plus 0.73 times f2 plus eta 1. Z2 is equal to 0.494 f times f1 plus 0.806 times f2 plus eta 2. You could write it out like that too.
So you said we call it estimated,
This is the estimated model.
and we have to just write it in board. We cannot get the output from R.
Well,
I mean, yeah, from R, but
so on the test, I might say, okay, here's a data set. Go estimate the model. write out what the estimated model is. And so you would do, you know, the fact analysis step, you would do this step, and then you do this step. And the reason why we want to be able to write out the model like this is so that we understand, okay, this is how factor analysis is saying that Z1 comes about, how Z2 comes about. But also, now we can start thinking about how can I interpret F1 and F2. So let's see here. So what would you say that F1 is essentially representing here? Relative to the goblet. So let me actually get that goblet. There we go. Yeah, it's kind of small. So X1 and X2 are at the top of the goblet. Let's actually just blow it up. X4 and X6 are at the bottom of the goblet, and X5 is the connection between the two goblets, or parts of the goblet. So what would you say then that the first common factor is representing? And think about what we have for principal component analysis. How we interpreted the first principal component.
The connection was X5.
Say that one more time, please.
Will be the connection X4 and X5 that have like the biggest values.
Yes, yeah. So X4, Z4, obviously is strongly related to the first common factor. And remember, these are essentially correlations. So that's playing a huge role. The other variables are playing an important role as well. And so you could just kind of say this is maybe just an overall measurement of the size of that goblet, where there's essentially more weight on that connection. That connection is very important. Let's look at the second common factor. Notice that the Z1 and Z2 have corresponding factor loadings that are positive. Z5 and Z6 are negative, and they're a little bit smaller in terms of that, what that correlation represents. Z4 itself now is not representing much at all. And so now here I would say, okay, I know 1 and 2, Z1 and Z2 represent the top, 5 and 6 represent the bottom. Just verify that. I'm sorry, excuse me. 4, excuse me, maybe I misspoke before. 4 is the width of that base. For some reason I thought it was this one here, but no, I was wrong. So 4 is the width of the base. And so basically, what common factor 2 is representing is a contrast or comparison between what's happening with that very top part, you know, in terms of the opening, how big the opening is, how wide the total cup part is, in comparison to 5 and 6, which is, I don't know, I guess you could say some measurements of the base. It's leaving out one measurement. But you know, if I was an archaeologist, maybe this might make some sense relative to my understanding of the science behind this. Now you might be wondering, well, wait a second, Chris, aren't we looking at factor analysis because you said we can come up with better interpretations of our dimensions of our data? And that's true. There's going to be one thing that we're going to be starting to look at after this example that allows us to actually change what those lambdas are. those lambda hats are. And if we can change those lambda hats, perhaps then we can come up with an easier interpretation than maybe what we have here. Okay. Let's look back here in the output some more. We have some parts of the output that look familiar to us relative to what we have for principal component analysis. Proportion var, the proportion of variance that common factor 1 accounts for. Then cumulative var is the cumulative proportion. So two common factors account for 78% of the total variation in our data. Now, for principal component analysis, we really focus on that. For factor analysis, actually, we don't. It's interesting to know that. And I give some information in the notes about how these calculations are actually made. But in the end, in factor analysis, you typically don't focus on that. We are going to focus on some other measures that help us make a judgment about, okay, is this factor analysis model really accounting for a lot of it, most of the information in our data? So stay tuned for that.
Is that the reason why, like, from the model, if you check in the model, we use factor is to be equals to 2, like, because we didn't pay that much attention on how much variation is actually contributing in terms of factors.
Well, okay, so I think you're getting at essentially, well, why did I use 2? Okay, and we're going to be looking at actually a hypothesis testing technique that will help us make that decision instead of looking at the total variance. But also, you've got to remember that factor analysis is not just concerned about the variances anymore. It's actually also interested in the associations as well. And so that's why it's not necessarily as widely looked upon. Now, inside of mod.fit2, we have different components. One of them actually ended up being correlation. So if I said mod.fit2 $correlation, I get the estimated correlation matrix, which will be exactly the same as if I use the core function itself. Okay? Note that there was a little bit of a typo in the notes. The program was fine, but the notes were not. And so what we might be interested in looking at then is as follows. Our factor analysis model says the correlation matrix should be equal to lambda prime plus psi. Well, how about we calculate the corresponding estimated values of this? So what I could do is I go into mod.fit2, and if I look at the loadings component, I can pull out my lambda hat matrix. It's a little bit, they structure some stuff in a way that I don't like. And if you remember, like if I had a matrix, let's call it A and R, if I did 1 comma and then put nothing after that comma inside of square brackets, this gives me my first the first row. If instead I would have just comma 1 there, that gives me my first my first column. If I actually put nothing in there and just put a comma, I get the entire matrix. And I urge you to, after class on your own, because we're running out of time, I don't want to go through the details, just execute that set of code. And you're going to get the factor loading matrix and some other stuff that we don't want. And so, but if I just say mod.fit2 $loadings, bracket, comma, and bracket, I just get the matrix itself. And so if I wanted to calculate lambda hat times lambda hat prime, I use my matrix multiplication symbol in R to do the multiplication. And then I use the T function for transpose. And then I can add to it a diagonal matrix that has all the specific variances. Remember again, uniqueness is a name for specific variances. And so in other words, I'm actually myself, you could say, manually calculating lambda hat times lambda hat prime plus psi hat. If my model was perfect and everything in my data was explained by this model, this matrix that I get in the end should be exactly the same as that. But we can see there are differences. If you remember when you first saw regression analysis, you learned about something called a residual. You would take, let's say your response variable was y. You would take y minus y hat, where y hat was the estimated value from your regression model. And that's called your residual. You might have called it E, for example. It's common notation. And you wanted those E's to be as small as possible, because that means that your model is fitting the data the best possible. If the E's were large, then that model is maybe not really doing a good job of fitting your data. It's not a good predictor. And so what we could do then, in this particular case, is how about we take that estimated correlation matrix that you would normally, the normal way that you would estimate it, subtract off what we get from our model, and now we have a version of factor analysis residuals. Just calculate it in a different way. But again, we want these residuals to be as close to zero as possible. The closer to zero, the better the model. And so we can see here that these values are fairly close to zero. And remember, we're working with correlations here, so we have a numerical scale that we can kind of understand. Correlations are between -1 and 1. All these residuals are essentially close to zero, except for maybe 1. Now, think of it this way. So you might be thinking, well, Chris, you're off by -0.036 here for the correlation between W1 and W5. How do I know if that's too big or if it's okay to represent, this is a good model? Well, think of it, let's say somebody told you the correlation between two things was 0.5. And then say, oh, whoops, sorry, I meant 0.53. Would that alarm you to see that much of a difference? Probably not. But if I have, let's say, 0.13, well, now you're, difference between 0.5 and 0.63. Well, okay, that's a little bit bigger. But if I told you, let's say, someone said the difference, I told you the first time the correlation was 0.2, and now the next time I said it was 0.8. Now you'd be worried. Okay, so think of that in your head when you're, trying to interpret these residuals. So overall here, this model seems decent. My only little bit of concern is that 0.13. But otherwise, using this tool, I'm mostly satisfied with this model. Okay, so we're out of time here. Let me come back.
Can you repeat one more time what would be the situation that we have the residual equal to 0 and those would be the same?
If the residual was 0, that would mean, let's say if I use the core function R to find the estimated correlation matrix. And then again, I use my model to find the lambda hat times lambda hat prime plus the psi hat. If I take if I subtract the 2 and the value for a particular element of the resulting matrix is 0, that says my model perfectly explains the information that was in that correlation matrix. It's getting at all the information. If it's not 0, then that's when I start to worry a little bit. And how far it is from 0 tells me how much I should worry. Okay, so what's next? I have my office hours. On Tuesday, we will continue with factor analysis. And looking further ahead, Friday, this week, at 5 p.m., that project's due. For your group, just email me one overall project. Please make sure to put all the group members' names in the project. And in fact, if you put that as the file name, meaning all the group members' names, that would be helpful for me too. Test number 2 is not too far away. It's 2 weeks from today. We will have the graphics section, the principal component analysis section, and the factor analysis section on that test. Okay? So that's all for today.